at a certain location, we could evaluate the slope of this circle at a given location. Let's say this is like 5, for example. However, there's two x equals 5 values or locations when you're dealing with something that's not a function. So if I'm going to evaluate the derivative here, I need to know, am I finding the slope at 5, 2, or am I finding the slope at 5, -2? So the derivative formula is just now going to involve x's and y's because we have to be more specific about, not just the x value at which we're looking for the slope, but the x coordinate and the y coordinate. Okay? So we're going to be finding the derivative of the function with respect to x. So on this first example, if I take the derivative of piece by piece, now the derivative of x squared is 2x. With respect to x, technically, and I don't know if I should say this now or later, it's the derivative of x with respect to x, which dx over dx would just be anything over itself is just 1. So we really don't almost even think about that. But on this y term, the derivative is 2y, but it's got to be kind of followed by this chain rule. The derivative of what's inside is dy dx. That what's inside was just the y, and the derivative of that is dy dx. Equals, derivative of 16 is 0. And so you almost can follow the chain rule all the time in cases where the derivative of x with respect to x is just 1, and we kind of have been doing that. But this whole thing, when you have multiple variables, we're doing it with respect to x. So the dx just kind of cancels, but we have this dy dx. And then we're just going to rearrange this and get dy dx all by itself. So if I subtract 2x from both sides, I get -2y dy dx equals -2x. And then divide by -2y. I'm going to get that dy dx just equals x over y. So I'm going to graph this. Graphing it on your calculator obviously requires that it be a function, so I'm going to have to solve for y. So if I subtract, give me 1 second, Liam. In order to type this in, I have to type in y equals plus or minus the square root of x squared minus 16 to see what this graph looks like. So it's going to have to come in 2 parts. So the positive square root of x squared minus 16 and the negative square root of x squared minus 16. I'll just do zoom 6 for now. So here's what this looks like. Does anyone know what this graph is called?
Hyperbola.
Hyperbola, very good. But we see it's not a function. And so anytime we want to find the derivative, we have to know not just the x value at which we want the slope, because if we were out here, we wouldn't know if we're getting the slope there or there. So if I take, for example, let's go 1, 2, 3, 4, at 5, let's say. So if I want to find the slope at 5, I have to specifically, is it 5, like what is it, 5 this value or 5 this value? So let me first see what happens if I find the value at 5. Okay, there's a point at 5, 3. If I want the slope at 5, 3, I have to plug in 5 for x and 3 for y, and I find out that the slope is 5/3 there. Yes? If I wanted it at 5, -3, I would have to plug in that point, 5, -3, and what's the difference in the slope down here? If I plug in 5, -3, I'm going to get -5/3, which you can see. This is a positive slope. This is a negative slope. Does that make sense?
So basically, it's just like what we did before. You don't need to know the y value, basically. You just plug in the x.
Previously, we didn't need to know the y value because they were all functions. So if I said, give me the slope at x equals 7, there was only one point at x equals 7. Now there are potentially multiple points there. And then he would say, okay, well, obviously the graph doesn't exist here, and so therefore the slope doesn't exist. So what happens if we plugged in a point? You can't plug in a point in this area because that point doesn't exist on the function. You have to be plugging in a point that exists on the original function. If I were to grab, the only any point that you're curious about, what the slope would be there? Right, exactly, because it looks like the slope should be what? Undefined, right? Because there's a vertical tangent line right there. And sure enough, the point is 4, 0, and it actually falls on both the plus and minus. The point is 4, 0. If you plug in 4 for x and 0 for y, you are going to get an undefined. So it kind of works all out nicely. That if it's going to be an undefined slope, it's undefined. So this is undefined for the sake of you're plugging in a 0 in the denominator. These are undefined simply because there isn't even a point you can plug in. Does this make sense? Okay? All right, Liam, question?
You answered it.
Good, okay. All right, so, gets a little uglier. We want to find the derivative of this. So we're finding dy dx. So everything with respect to x doesn't need the chain rule dx dx, although if you want to think of it, you can. But if I start taking the derivative of just this first piece, what do I need? Product. So I have first times derivative of y is just dy dx. Yes, 1 followed by a dy dx. Plus the second y times the derivative of the first would just be 2x. And there's no need to follow that one up with dx dx because this is already with respect to x. Plus, on the second piece here, we also need a product rule. So our first times the derivative of x is just 1 plus the second x times the derivative of the first is what, Nathan Z? What's the derivative I'm going to write down for y squared?
2y dy dx.
Very good. Equals the derivative of negative 2? 0. So we take the derivative of everything. Now we need to clean it up and we need to get dy dx all by itself. So the terms that are already dy dx's, I'm going to leave them on the left-hand side. So that'll be an x squared dy dx plus a 2xy dy dx equals, and I'm going to subtract the non-dy dx terms away. So that'll be a negative y squared minus 2xy. So I subtracted that over and I subtracted that over. Now if I'm solving for dy dx, what do I need to do to get there to be only one of them? Factor it out. So I'm going to factor out a dy dx and I'm left with x squared plus 2xy. And then just divide that binomial over. This one? No. This one. You take the derivative of every piece. Good question. So you take the derivative of this, take the derivative of this, equals the derivative of that is 0. Yeah, we didn't really have to worry about both sides before because we always had, like, let's go back. That's a good thing to think about. We technically were doing it, but we had like y equals 5x squared. So we were taking the derivative of y with respect to x. So this derivative, we wrote y prime, but that was also dy dx. We were technically taking the derivative of y with respect to x and getting dy dx, and it was already by itself. Do you follow? And this was 10x, technically followed by dx dx, but you would never write that because it was already with respect to x. Does that make sense, Lily? So you could think of it now in hindsight, we were technically always taking the derivative of both sides. It's just that the y, or f of x, or whatever it was already standing alone. And so we kind of didn't think of it that way. So we're just dividing this binomial over. And there's our more complicated derivative that would help us find the slope on this curve at any xy point. So whatever point you want it at, you would just plug in that point and get your slope at that point. Jalen.
Could you factor out the 2x, y, and
You could clean these up if you want to, and you'd have to kind of see what's. Does it simplify more? Is that what you're saying?
Yeah.
Oh, it would. So if I factor out a negative y,
No, the 2xy. Do the 2xy on the top and the bottom.
so cancel them. Like chop off a piece of a polynomial. Is that what you're suggesting?
No, factor out the 2xy on the top and the bottom, and then you can cancel them.
So negative y minus 1.
Yeah, minus 1.
Where are you pulling?
Where are you pulling a 2xy from if only one term has it?
Oh, never mind.
If anything, you'd factor out a negative y, and you'd have y plus 2x. And on the bottom, you could take out an x, and you'd have x plus 2y. There's not really anything to do. Did you find your mental?
Yeah, I don't know.
Josh, are you good? Okay. Okay, here we go. Derivative of cotangent. Negative cosecant squared. Are we sure about that? Why do I think it's negative cosecant cotangent? Oh, no, negative cosecant. No, it's negative cosecant squared. Oh, I didn't hear the negative. Negative cosecant squared of y times what? dy dx equals derivative of x is just 1 minus dy dx. Again, we've got to solve for dy dx, so we have to get those all together. So I'm going to add this guy over, so it'll be dy dx minus the cosecant squared y dy dx that's already over there equals 1. So I added that dy dx over and I put it out in front. Again, factor out the dy dx. And I get 1 minus cosecant squared y. And then just divide that over. Good? Any questions? Here's another one. E to the xy. Let's go with Kyle. What's the derivative of e to the xy? Just this piece.
Would be ln of u times e to the xy times.
Are you following the exponential rule that you learned last night?
Yeah.
Okay, when it's, so we learned those two exponential rules, but still when the base is e to the x, I don't want you to overcomplicate it. Like I showed you kind of the long way of how this rule still makes that work out, but the derivative of e to the x is just e to the x. Do you follow? Same thing with ln of x. Don't overcomplicate that one as a log one. These are more used, well, these are only really necessary when it's not a natural log or it's not a base of e. If it's a base of e or it's a natural log, still go with this easier method. Okay? And I will be honest with you. We're not going to be tested on these. Okay? I'm going to keep those off of things. It's just, I wanted you to be aware that there's other derivatives out there for logs that have a different base other than e, and for exponential functions that have a different base other than e. So these will come up a lot, and they're a lot simpler. These really won't. I just wanted you to get the practice of using those new rules.
You can still do it. Like ln of e is 1.
No, I know.
And then it's like the same thing. It's just, onto the
This long one?
Yeah.
Oh, well then go for it.
Because you're only use 1 times or e to the xy times 1
Mhm.
dydx.
I know, and I showed that too in the video, of how these rules still work for what we already know, but I don't know why you would do that. These are just easier. But you can. I'm not going to stop you. So, Kyle, so e to the xy is just e to the xy times what, though?
dy over dx.
Someone help him out. Winter?
Times y and dy over dx.
What rule are you using? Chain, but when you take the derivative of what's inside, this requires the product. So first times derivative of the second, dy dx, plus the second times the derivative of x, which is just 1. Follow? Second term, the derivative of x squared is just, what, Ellie? X squared, the second term? 2x. Minus, and our next term, Zach? Perfect. Equals, what, Haley? 0. Good. So now we just have to work towards getting that dy dx all by itself. Can't really happen. We got to kind of free this one up by distributing that e to the xy. So I'm going to distribute this through. I'm going to have x e to the xy dy dx plus y e to the xy plus, leave everything else the same. And I'm going to move away the non-dy dx terms. So keeping the left-hand side just this term and this term. Subtracting this over, subtracting that over. Factoring out my dy dx. Copying the rest. And then dividing over that binomial. Questions on that one? You want to practice on your own? Or do you want me to keep going through them? Raise your hand if you wanted to try them on your own. Raise your hand if you want me to keep going through them with you. Okay. If you want to try them on your own, don't listen to me. Actually, you should probably work backwards. Just work on a different problem and just ignore me. Raise your hand if you're just going to go along with me, straight in the air so I know who I'm talking to. Okay. So, first term here. Bring your 3 out in front, will be 6x squared. Plus, second term here, bring power rule. It'll be 9y squared dy dx equals 0. So just getting dy dx all by itself, Zach, what do I have to do first? If I'm trying to isolate this, getting this all by itself, what over here do I have to move away first? Yep. Ellie, what would come next?
I did.
Oh, you did?
Yes.
So what did you do next?
I divided
Good. And what did you simplify this to?
-2x squared over 3y squared.
Perfect. Good, good, good. Any questions on that first one? All right, second one. This is technically xy to the 1/2 power. So when I first go to apply a rule, Kyle, what rule do I apply first? This one. Oh, sorry, never mind you. Power rule, yep, followed by, right. So 1/2 out in front, xy to the negative 1/2, times the derivative of what's inside. And what's inside here is a product rule. So that would be first times the derivative of the second, dy dx, plus the second, y, times the derivative of the first, which is just 1. Close your bracket, equals. I should have moved over. Oh.
Isn't it x squared first?
Here?
Yeah.
No, because I'm just doing the derivative of what's inside.
Oh, I thought you were already doing x.
Oh, no, I haven't gotten there yet. So now on the other side, this first term requires a product, which is first x squared times dy dx, derivative of the second, plus your second, which is y, times the derivative of the first, which is just 2x. The plus 1 just has a derivative of 0. So in cleaning this one up, I am going to, this is the same thing as 1 over 2 root xy. I'm just really rewriting to give myself space here. You have to be willing to write a whole new line even though you're not changing much, just to like take your breath. Because if you try to do too much at once, this is not going to be good. And I think that's kind of the balance that is different for different people. But be willing to just do a little more labor writing it out so that you can kind of give your mind a moment to just process what's being organized here. Again, here with the dy dx being locked up in brackets, I can't really do much to free it up and get it with this other one until I distribute. So that's going to be x over 2 root xy in front of the dy dx plus y over the 2 root xy. Again, I got to get my dy dx's on the same side, so I'll subtract this one over to the left, and I'll get rid of this one over to the right. So x over 2 root xy dy dx minus the x squared dy dx equals 2xy minus this guy over. Factor out your dy dx. X over 2 root xy minus x squared. And then divide over. What happens when you divide over? We have a complex fraction, which luckily comes with the mini denominators inside having the same, being the same thing. So I can just clear by 2 root xy and 2 root xy. And hopefully I'm done here, although you never do know. So when you distribute up top, you get 4 xy root xy on the first term minus y on the second term. On your denominator, when you distribute, you get just x minus, on the second term, 2x squared root xy. If you wanted to, you could GCF a y out of the top and an x out of the bottom, but you're not going to see anything different or cancelable. Okay? Do we understand the process? What rule comes first over here? Liam? Power. The 2 has to come out in front, leave everything else the same. Times the derivative of what's inside. So the derivative of sine pi x is cosine pi x times pi, right? Derivative of this, cosine, I'm going to give big brackets here because the derivative of what's inside is a polynomial. So cosine pi x times pi, I'm going to put the pi out in front. Plus, technically, but then the derivative of cosine is going to be a negative sign, so it's going to be minus a sine of pi y times the derivative of what's inside, which is pi dy dx equals 0. Thank God. So, which way do I want to go with this? Actually, I can divide this whole thing on both sides, can't I? And this will be negligible, right? 0 divided by this. So if I divide by this, I'll show it just so if you look back, you see. If I divide by that on both sides, it's going to cancel. And then I'll just have pi cosine of pi x minus pi sine pi y dy dx equals 0. I can add this over if I want. That's what I'll do because I'll like to keep everything positive. And then divide that over. So dy dx will equal pi cosine of pi x divided by pi sine of pi y. And your pi's will cancel. Cosine pi x over sine pi y. And the last one. I'm going to go down here. Derivative of x is just 1. Derivative of secant is secant tan. So secant 1 over y, tan of 1 over y. But then we have to multiply that by the derivative of what's inside, which is the 1 over y. So, or you could say that that's y to the negative first if you want. Y to the negative first. So the derivative of that would be negative y to the negative second dy dx. So what would we do first to clean this up? What do you think, Nathan? Yep, I would divide this chunk over. Very good. 1 over the secant of 1 over y, tan of 1 over y equals, I don't know if you want to do, I would probably change that negative exponent to negative 1 over y squared dy dx. And then I would just get rid of that fraction by multiplying by the reciprocal, which is just going to be negative y squared over 1. So you're going to get negative y squared over secant 1 over y, tan of 1 over y. I will say on this one, with a secant on the denominator, that's the same as what in the numerator? Cosine, right? So they may write that as a cosine in the denominator. They may mess around with that a little bit, trig-wise. Okie doke? So about 10 of those to practice for